What the heck is up, everyone? It's Jacob here, and in this video I just want to make kind of a quick video explaining the very basic fundamentals of electricity and what is actually happening when you have electric charge flowing. So this is just going to again be a very basic video about electricity. I see a lot of other videos and they kind of use this like water analogy of water flowing through like a pipe or a plumbing system. And that analogy works good to a certain extent, but I feel like there's a lot of obscurities and it doesn't really paint the full picture of what's actually happening. So let's get started. And to understand electricity, first we have to understand the idea of a charge. So I have here three subatomic particles. Subatomic just means these are what make up pretty much every atom that exists. So any atom of any material that you can think of is made up of these three particles, and these all together will collectively form an atom. So of these three particles, the electron is the only one that is fundamental, which just means it can't be broken down anymore. The electron is an electron. You can't break it down anymore, whereas the proton and neutron, these two particles can be broken down into what are called quarks. That's way beyond the scope of this video. I just wanted to kind of throw that in there. But anyways, there are two types of charges. There's only two types of charges. So charge is just a fundamental property of particles, of subatomic particles. It's something that's there. We really don't know a ton about it. We just know a lot about how it behaves. But we don't really know to this day what causes charge or why some particles are charged and some aren't. So it's still one of those great mysteries. So there's two types of charges. There's a positive charge and a negative charge. So proton, in an atom, a proton has a positive charge. It has a charge of what we would call E. That carries a value of 1.67 times 10 to the negative 19 coulombs. And coulombs is just a unit of charge, kind of like you might have a unit of mass. You might use pounds or kilograms. We use coulombs for the unit of charge. So not that that really matters, I just kind of want to give you guys that information. Also, we have the neutron. So the neutron is overall neutral. There are charges inside of it. Those quarks are charged, but altogether, when you combine them, the overall charge of a neutron is neutral. And so it just possesses no charge. So there's only really two types of charges, positive and negative. All right, so now that we understand the two types of charges and that some particles are charged, well, let's look at some of the properties of charge. So charge has a few properties that we need to understand. First, just so you guys know, in this video, red will represent a positive proton, while blue will represent a negatively charged electron. So that's what we're using throughout this video. So on the proton, you can see in a region around that proton, there is an electric field which is pointing radially outwards. So in any area around that proton, within a certain proximity of that proton, it has an electric field pointing away from that particle. Likewise, on the electron, it has an electric field pointing radially inwards. So at any given point, it has an electric field line pointing directly into that particle. So basically, if you don't know what a field is, that's all right. We'll discuss that in the next slide, because a field is kind of a hard idea to understand. It's not something that you can really see, but I have a good idea of what can give you guys an understanding of what a field is. So just understand that for now, positive charges have an electric field permeating outwards from that charge, while these negative charges will have a field pointing inwards. Okay. So here we have some more properties of charge. Down here, I'm demonstrating that like charges will repel. We have two positive charges down here, two protons, and they will have a repulsion force between them. They will want to repel each other, and they will push away from each other. Likewise, with two negative charges, if they're like charges, they will repel each other, so they will have a repulsion force between them. Their electric fields interact with each other. We'll see that in the next couple slides. Their electric fields will interact with each other and they will repel each other. So like charges will repel. On the other hand, unlike charges will want to attract. They will have an attraction force between them and they will pull towards each other naturally, just from their electric fields interacting with each other. So those are just a few properties of charge that we need to understand in order to kind of understand what's really happening with electricity. All right, guys, so hopefully this will help give you an idea of a field. So I'm gonna discuss, I'm not really gonna discuss magnetic fields in this video. Magnetic fields will be in a whole nother video. They're different from electric fields, so magnetic and electric fields are not the same at all. They are very closely related, but they are not the same thing. I just want to make that clear. So we're not really going to be discussing magnetic fields in this video, but because it's very hard to explain an electric field, I figure a really good analogy, they're pretty much the same, but just a tiny bit different. One's magnetic and one's electric. Without a doubt, all of you have played with magnets before, and you know that if you have magnets, you can when you bring them close to each other in one orientation, they will attract each other, and if you flip one of the magnets, they will repel each other. So we can see that here in this picture here, these magnets have their opposite poles near each other, and they have an attraction force between them. So these magnetic field lines that exist around these magnets, so there's magnetic field lines which are in an area, a region around that magnet, near that magnet. Just like in the previous slide, we had these electric field lines right here that existed in an area around the charge. We have the same thing here. We have these magnetic field lines that exist in an area around the magnets, and these field lines will interact with each other. You can tell when you bring two magnets really close to each other, they will start to have either a repulsion force or an attraction force, and those magnets will want to repel or attract each other. And that force is due to the magnetic field that exists around these magnets. It's something that you can't really see, but you know it's there because you can feel the forces between those two magnets. Those fields that exist around the magnet are magnetic fields, and they behave in a very similar way to electric fields. If you brought two charges next to each other, they would behave the same way. If you brought two protons really close to each other, they would want to repel each other. Likewise, if you brought an electron and a proton near each other, they would want to attract each other, just like the same way the magnets would. And that's due to the interaction of the electric field. So hopefully this will kind of give you guys an idea of an electric field. It behaves just like a magnetic field. Again, they're not the same, they're different. That's a whole nother video. All right. So let's look at how charges behave in an electric field. So if these arrows here represent some electric field, they're pointing to the right. So all these external arrows are an electric field, not a magnetic field. They're an electric field. And in an electric field, this positive charge here it will have a force on it that will be in the same direction as the field. So if we have an electric field that's pointing to the right here, as we can see, this positive charge, this proton, will want to accelerate. It'll have a force on it pushing it to the right. It will have a force that pushes it and accelerates that proton to the right. So the electron over here will have a force that pushes it opposite the direction of the electric field. It will want to move the opposite direction of the electric field. So it has a force that opposes the electric field, and that electron will kind of move in the opposite direction of that electric field. So those are how those two charges will behave in an electric field. A positive charge will move in the direction of the electric field. It has a force in the direction of the electric field, whereas a negative charge will have a force that pushes it in the opposite direction, away from that electric field. So now we can discuss electric potential. So the electric potential here is kind of getting into voltage. Voltage is electric potential, and I'm going to make an entirely different video just on electric potential and what voltage actually is. Again, there's some videos out there that use the pressure, like the water analogy, and they explain it as pressure in a pipe, and that's a kind of a good analogy, but it doesn't really explain the full picture of what's happening. Again, so electric potential is voltage. They are the same thing, but so let's kind of explain what electric potential actually is, what this means. If we look here, let's assume this thing here, this object is a ball. So this black object is a ball. If you pick up a ball and you raise it, let's say 10 feet in the air, that ball will have what's called potential energy. So potential energy is just stored energy. Essentially, that ball has energy stored in it, because if you release that ball, it's going to want to fall to the ground due to gravity. It has a force. It has a downward force acting on that ball. from gravity. So gravity is going to want to pull that ball downwards. So when you raise it up into the air, it has a higher potential. This ball will have a higher potential when you raise it in the air. Likewise, when it falls down to the ground, it will be at a lower potential. So it has more potential energy when you raise it up in the air. The gravity will have a downward force on it and will want to pull it down to the ground where it has zero potential, or it's at a lower potential. So over here we have a very similar situation going on. We have a negatively charged electron, and we have it between two plates. Now these two plates have a potential difference, as we can see, of 100 volts. So let's assume the top plate up here, it's at a higher potential, so it's at a higher voltage, it's at 100 volts, and this lower plate down here is at a lower potential, it's at 0 volts, let's just say, and these are relative to each other. Electric potential is a relative quantity. Voltage has to be relative to 2 points. You can't just say one point is at some potential. It has to be between 2 points. I'll discuss that more in my electric potential or voltage video, but for now I just kind of want to give you guys this idea. So if we have this electron that's sitting between these two plates here, so one's at a higher potential and one's at a lower potential, the electron again moves kind of like in this counterintuitive way. This gray line over here would represent the electric field present between this potential difference. So when you have a potential difference, there will always be an electric field, and that electric field points, as we can see, this electric field here points from the higher potential up here down to the lower potential. So the electric field will point always from high to low potential. But if you remember from a couple slides before, the electron wants to move opposite the direction of the electric field. So the electron will actually want to move upwards. It has an upwards force on it. As we can see, this arrow here on the electron is pointing upwards, and that's the electric force on that electron. That electron wants to move towards the positively charged plate. It has an electric force on it because there's between these two plates with the potential difference, there is an electric field here, this gray line pointing downwards, and that electron wants to move opposite the direction of the electric field. It has an upward force on it. So this electron will want to move from a lower potential to a higher potential. It's kind of opposite of what's going on over here with the ball. Remember, the ball moved from a higher potential down to a lower potential. It wants to fall back down to the earth, whereas the electron wants to go from a lower potential to a higher potential. So it's opposite. So let's look at conductivity. So here I've just kind of drawn out this atom. It's an aluminum atom. So this represents aluminum. So what makes a certain material conductive is if it has electrons which it can easily give up. So we can see here that in the center here we have the nucleus. Now the nucleus consists of protons and neutrons, so overall it has a positive charge. That's why we've drawn it red. The neutrons don't really affect the charge, and what happens is this, because it's positive, it has an electric force on these electrons. Remember, since they're opposite charges, these electrons have a negative charge, and this nucleus, which consists of a lot of protons, is overall positive. So there's an attraction force going on here between these individual electrons and this proton. So this proton is really tugging on these electrons close by, and it's tugging on these ones out here as well in these outer shells, but not as much. They're a little bit further away, so that the pull on those electrons isn't as strong. And when we get way out here, we get to the valence electrons, and these electrons have very little attraction to the nucleus at the center, so they're not pulled as strongly by the nucleus. So if we place this atom in an electric field, so let's say we had an electric field pointing to the right here, what would happen is there would be a force between these electrons, the normal force that we have between the electrons and this nucleus. They're attracting each other, but if we have a strong enough electric field out here, or a potential difference, this electric field will actually have a force on these electrons as well. And these outer electrons, if their valence band and their conductance band overlap, which basically means they're not bound very strongly and that they can easily be removed with little energy, these outer electrons will actually be stripped off of this atom. So these outer electrons will be pulled away from the force. We would actually, if we had an electric field pointing to the right as we do here, we would have on each of these outer electrons a force pointing to the left. So these electrons would actually be stripped off the atom, these outer electrons, and they would want to move to the left. It's a really bad arrow, but they would want to move to the left due to the external electric field. And we'll get into actually how these electrons flow in the next couple slides. It'll make more sense. But I just kind of want to show you guys what makes certain metals conductive. Basically, it's when these outer valence electrons can easily be removed, and when the electric force from this external electric field here, when it is strong enough to actually overcome the electric force between these electrons and its nucleus, when it's stronger, it can pull them away from the atom, and that is what causes that atom to become conductive, or it allows electrons to flow between that atom. So let's look at how charge flows in a basic circuit. So if we have this battery here, again, the positive side is at a higher potential. So the positive side is at a higher potential, and the negative side is at a lower potential. So relative to each other, these two sides, this side here would have a higher potential. And so what happens is these gray lines here represent the electric field. So this whole thing is a wire. It's just a wire. And these gray lines would represent the electric field present in that wire. These little gray arrows here represent the direction of conventional current flow. You might have heard that term thrown around. There's conventional current flow and electron current flow. And electron current flow is just the way the electrons are flowing. Conventional current flow is the way it's kind of a way to think of positive charge carriers. I don't really want to get into that here. It's a little too advanced. We'll maybe get into that in a current video where I talk about current in more detail. But essentially, these gray arrows here represent the direction of the electric field. Remember, the electric field from a few slides back, if we go back here, this gray arrow represents the electric field here, and it points from a high potential up here to a lower potential. So the electric field always points from a high potential to a lower potential. So in this circuit, the higher potential here starts on the positive side, and these gray arrows are going to be pointing along this wire to the negative side, which is at the lower potential. So this is the direction of the current, the conventional current, as well as the direction of the electric field present in this wire. So inside the wire, there's a bunch of atoms. The actual copper wire, whatever material this wire is made up of a bunch of atoms. We'll look at that in the next slide. But it's made up of a bunch of atoms, and these electrons will flow between the atoms. So it's basically going to the electrons are going to be pushed off of atoms and be pushed back onto atoms. I'll explain that in the next slide. It'll make more sense. But essentially, because there's an electric field in this direction that these gray arrows are pointing, the electrons, of course, are going to want to move opposite the direction of the electric field. So they're going to move from the negative side, and they're going to flow in the direction of these black arrows here. They're going to flow to the positive side. So the electrons are actually going to start flowing from negative to positive. And so it's easy to think of these electrons kind of as flowing as we see in this picture, but it's not just a stream of electrons flowing. And that goes kind of back to that water analogy. A lot of them will say, it's charge carriers flowing like in this direction, and it's just a bunch of charge carriers. Here in this next slide, we'll actually see what happens in this wire. Again, the wire is not just made up of a bunch of electrons. The wire is made up of atoms, which have electrons spinning around the atom in an electron cloud. It's kind of what we call a sea of electrons. So let's look at that. So here, this is kind of like a blown up image of the wire. So if let me clear that line there. If we look at, this is just a very small, like, close-up snapshot of the wire. So these black borders here would represent the edge of the wire. So the wire is made up of a bunch of atoms. Again, these are just aluminum atoms that I've drawn in here. And essentially what happens is we can see there's a bunch of atoms really close, compact in this wire, and that's what makes up the wire. Obviously, it's made up of a bunch of atoms, whether it be aluminum or copper, gold. It doesn't really matter what the atoms are. And so here on this end of the wire, we have a higher potential, and on this end of the wire, we have a lower potential. These gray arrows again represent our electric field. So the electric field points towards the left. So these electrons in this wire are going to want to move towards the right, or opposite the direction of that electric field. So we can imagine this as just a really close-up picture of that previous slide that we saw here with this battery, if we zoomed into this wire a lot, here's what we would see. We would see these atoms here, and what's actually happening is these electrons they're not really flowing. It actually takes a really long time. It takes a very long time for an electron to make it from this point over here to this point over here. If you were to track this electron as it started on its journey over here to where it ended up over here, it would take a very, very, very long time. And here's why. Here's what's actually happening. These electrons are pretty much bouncing from atom to atom. So the electric field, again, is going to influence, it's going to pull on these electrons in these outer valence shells. And so it's going to take, let's just say, this little electron over here, and it's going to pull it, and it's going to throw it into this valence shell of this atom, this aluminum atom over here. And so since it gained an electron, it's going to want to kick one off, and it's going to go there. Overall, you can see they're moving in a rightward direction, and there's lots of collisions. These electrons will hit, they'll run into these atoms, they'll run into other electrons, they'll have a lot of forces slowing them down, so they'll have a lot of collisions. It's not like they're just freely just moving from atom to atom. They're constantly moving and being slowed down, so they're constantly colliding with other electrons. They're not really colliding with the electrons, but they're getting really close, and their forces are pushing them apart. But they're essentially what we'd think of as colliding. So these electrons are colliding, so they're constantly moving in the rightward direction. Overall, we can see these electrons are moving to the right, opposite the direction of the electric field, but not in a very efficient manner. And this is what's actually happening. These electrons bounce from literally just atom to atom, and they just keep, knocking atoms off, or knocking electrons off of the shells of atoms, and they just keep replacing them. So it's kind of like a chain reaction. You can see we have a electron starting over here, and it goes into this atom, then it bounces into this shell. This atom gains an electron, so it's going to want to kick one off to this one kicks one off to here, and it just so on and so on. It just keeps going. If you follow these arrows, it kind of shows the path that an electron might take. And of course there's infinitely many paths. It can go along the path. It can choose whatever atom it wants to go into, but that's essentially what's happening. Is the outer shell of these electrons has electrons which can easily be removed. Their force, their attraction force to this nucleus isn't as strong as the electric force from this external magnetic field that we see out here, this gray, not magnetic field, but electric field. So this external electric field is influencing these outer electrons and kind of overall pushing them to the right. And they really just flow from atom to atom to atom, and that's why it takes so long. The electron itself, it's not like there's just, in this picture, we just see a bunch of electrons kind of flowing, but that's not what's really happening. It's electrons being, kind of passed on from one shell to the next shell to the next shell of all these atoms, of the actual copper atoms or aluminum or whatever that wire is made of. Those are the atoms which are passing on those outer valence electrons, and that's actually what causes that current to flow. The current is those charge carriers, or those electrons flowing. And actually the current is the amount of charge, the amount of the coulombs per second. That's actually the definition of an amp, is it's coulombs per second, and that's how much charge you have flowing in any given amount of time. And we'll talk about that later on in a current video where I talk about current in great detail, but that is essentially what is happening here. And that's pretty much the end of it. I just kind of wanted to show you guys that real quick. That is what is actually happening in a very basic circuit. And this is just DC here. As we can see, we're using a battery. AC circuit is exactly the same, but of course it alternates many times a second. There's much more other aspects of AC circuits that we haven't really discussed in this video, and I'll do a whole other video on AC circuits later. It's a bit more complex, but it still behaves the same exact way as this, but it just kind of flips its polarity. Everything flips and goes the opposite direction every 60th of a second or whatever it is, depending on where you're located. So that pretty much wraps it up for this one, guys. I hope this gave you guys kind of a good conceptual understanding of what's actually happening when electricity flows through wires and what electricity actually is. It's the flow of electrons between the shells of atoms. We can see that it's just electrons going from shell to shell of atoms, and it's influenced by this potential difference, what we would call later on as voltage, and that creates an electric field which essentially just pulls electrons off of atoms. So that's pretty much just just basic electricity I hope you guys enjoyed this one, and as always, have a good one.